circular economy on a sustainable basis and the role of chemical engineers, presented by the University of Calcutta Chemical Engineers Alumni Association.
To start off with the inaugural program, I would like to invite to the dais Mr. Kaushik Ganguly, the head of the Chemical Engineering Department of the University of Calcutta. The Vice President of the Chemical Engineers Alumni Association and a retired teacher of the department, Professor Partho Shorati. Our honorable guest of honor, Professor Shuddha Shoktabasu, the former director of the Council for Scientific and Industrial Research's Central Institute of Mining and Fuel Research, Dhanbad, and the director of the Institute of Mining and Material Technology, Bhubaneswar.
I would like to invite to the dais our respected chief guest, Mr. Robin Mukhopadhyay, the Executive Vice President of Strategic Initiatives and Projects, Haldia Petrochemicals Limited. And last but not the least, our dear Professor Ashim Kumar Dev, a teacher of the department and the Secretary of Calcutta University Chemical Engineers Alumni Association.
Please welcome Professor Shuddha Shoktabasu. I now ask Ms. Shana Roy Chowdhury and Ms. Onkita Mundul to welcome Professor Partho Shorati and Professor Shuddha Shoktabasu with a bouquet of flowers each. Now request our beloved Kaushik Ganguly sir present us with the
চারদিকে যে অবস্থা আছে তাতে যে কোনো একাডেমিক ইনস্টিটিউটে ডিপার্টমেন্ট এবং অ্যালামনি অ্যাসোসিয়েশনের মধ্যে হ্যান্ডশেকিংটা বোধহয় ক্রমশ বেশি গুরুত্বপূর্ণ হয়ে উঠছে। এবং এই পরিপ্রেক্ষিতে এটা আমি এখানে জানাতে চাই যে আমরা বোধহয় আমাদের দুটো যে অর্গানাইজেশন, একদিকে ডিপার্টমেন্ট এবং আরেকদিকে অ্যালামনি অ্যাসোসিয়েশন, এর মধ্যে হ্যান্ডশেকিংটা বেশ ভালো। এবং ডিপার্টমেন্টের তরফ থেকে আমরা মাঝে মাঝেই, এটা সবাই জানেন, তাদের প্রচুর চালায় এবং তারাও যথেষ্ট করে। এবং আমি আশা রাখবো যে এই কোঅপারেশন আরও বাড়বে এবং এই মিউচুয়াল পার্টিসিপেশনের ফলে কতটুকুভাবে বলা উচিত যে মিউচুয়াল পার্টিসিপেশন না থাকলে আজকের দিনের মধ্যে একটা সময় এসে গেছে যেখানে ডিপার্টমেন্টের যাবতীয় অ্যাক্টিভিটি ডিফারেন্ট ভেরিয়াস রিজনস সেগুলো আস্তে আস্তে এফেক্টেড হচ্ছে এবং এই হ্যান্ডশেকিংটা ক্রমশ অত্যন্ত গুরুত্বপূর্ণ। সুতরাং এই আশা রেখে আমি আমার পক্ষ থেকে ফর্মালি ওয়েলকাম জানিয়ে
Thank you, sir. I will now invite Professor Partha Ray to talk to us through the symposium.
Welcome all of you. This symposium series started about 2 years back. In 2019, we had the first session in 19. On 2020, we could organize it because of the COVID. 21, we had it primarily online, and this year we have come back. This particular symposium was organized in order to come, in order to let the alumni of this department come in close contact with the current department and also among themselves and share their experience of life in all types of forms. The symposium invites every alumnus to participate by contributing something, contributing their experience and also contributing financially. The object was that this kind of interaction would increase the interaction among the students, alumni, as well as among the alumni themselves. And we know that many alumnus have become connected to other people through this alumni association and through these programs. Now we invite every alumnus to contribute their experience, and that experience did not necessarily be something very academic. We are not in this symposium, we are not asking for papers to be of the caliber that has to be published in journals like ASDG or so. We are inviting experience and knowledge, that vast amount of experience and knowledge that our alumni have gathered and they have at their disposition, which they can share with everybody else. So it's not just for only academic papers, it's for other industrial papers other experiences which may or may not be related even to chemical engineering. Many of our alumni work in IT sector, many work in finance, many work in other sectors also. Their experience in those sectors are also important and useful, and we want to share them. This is an inclusive one. We want everyone to come here and share, everyone to take part in it. Because of that, I was reluctant to put any name to the symposium, except that it is annual alumni symposium. Usually, however, all these symposiums or seminars, they usually take out a kind of specific subject. But I wanted this thing to be a broad-based one where everybody can participate. Let's think of it that this is not a World Cup in football where the principal thing is football, but it's a kind of Olympics where every sports, from every side is happy to be welcome. So I was reluctant to put in any kind of tag to this, but I was told, and I think that is justified, that unless a specific tag is put in, it's difficult to find sponsors. So I do not insist on that in putting a tag on this thing, but I would like everybody to realize that this is for everybody. It is not restricted to any particular topic, and every type of experience or every type of contribution will be welcome over here. I had been in charge in the first year. This year, Sujit has more or less taken up all the part for gathering the papers and things like that. And Oshin here has taken up the job of organizing the things at ground level and this all. So we must thank them for putting in so much amount of time and effort. There are many others who have taken part and have added to this effort to make this thing a success. I thank them all, and I welcome you all to this thing, and hoping that this one remains an annual event for a long time to come. I hope the next event we can organize about a year later, in December 21, 22, 23. That one will be Thursday, Friday, and Saturday next year, just prior to Christmas. And thank you all.
Thank you very much, Professor. Light has always been seen as a symbol of positivity. And with that note, I now request everyone present on the dais to come down for the lamp lighting ceremony, which will also be accompanied with a short inaugural song to start off with an auspicious and positive note. our honorable guest of honor, Professor Symposium-2022, please address the audience. Sir.
Respected dignitaries of the dais, respected all my teachers, Pranam Home Government, all my respected alumni, and the junior friends, current students, and any other dignitaries who are invited to today's gathering of Chem Engineering Alumni Association program, a very important circular economy. I'm going to, of course, give a talk on this, but maybe few things I can just give an introduction. If you think of how the mother nature, we call it mother, which is feminine gender, which is starting with Aristotle. So Aristotle's concept was this earth having rivers, which is like a veins and arteries of the body, which gives life to the body through water. And then there is a vegetation, and there are many other concepts that he explained that how the earth should be mother earth, how it is linked to feminine gender. It's all given to us. This concept was like this till about 17th or 18th century, when 1840 Francis Bacon gave, we started finding out, of course this was going on for some time, but not commercial level, started doing mining and taking advantage of all the deposits that we have, that the earth is not anymore feminine, it's masculine, because it has got all the iron ores, it has got all later crudes or petroleum, fossil fuel, coal of course is there for a long period of time, and coal, and so on and so forth. And we started, and there is nothing wrong to use the resources of Mother Nature, which is sort of became masculine gender at that time, of the concept of 1840, 1850 I'm talking about, and do as much as mining in all respect as possible. And that's how we have been using the resources of art. But today we understand that with this comes a lot of problems, and which all we see that first of all, this is limited resource. Second, we generate a lot of waste, whether it's a solid waste, liquid waste, or gaseous waste. And then we are actually losing a lot of energy, which we know from the first and second law of thermodynamics, the third law, zeroth law of thermodynamics, to the universe. And the word sustainability coined about 50 years back, that we need to be sustainable. So sustainability is, and the circular economy goes side by side. Many of the young people, I was also there at this, in this hall, gave all my exams, I remember here, that we were all thinking of doing equations, mathematics, and chemistry, chemical engineering, thermodynamics, and whatnot, mass transfer, heat transfer. At that time, it was only important, and that is what is science and engineering about. It is not really. You have to be a great thinker and great philosopher to be able to do well in your life, and to be able to do well for your country and for the world. So, if you don't think of this part of the whole So I will be using SDG quite often, which is coined by UN, and they are given 18 goals, sustainable development goals, which every country should take it forward. So that concept just have now come. The UN has started it about 10 years back, and now they are forcing it that circular economy is part of it. But for us, it is nothing new, and we have been doing it with recycling so many things in our house. But we are part of the whole world. We are also sometimes copying this development model that Western society has already done, and they have done a very marvelous job. I'm sure all of you, healthcare, to transport, to material development, they have done extremely well, and we have copied, and we are also working with them, and we are also developing with them. So, although this is there in our society already, simply Kavadi those who are collecting newspaper, those who are collecting bottles, those who are collecting old utensils, they all goes through a circular economy in our country. But I think we need to be organized now, because we have been having refineries, we have been having chemical industry, metallurgical industries, food, agriculture, everywhere. The circular economy, circularity means circularity in the economy or the process is possible. We generate in our country, I'm not about India alone, we generate about 12 million tons of e-waste per annum. 12 million tons of e-waste. E-waste means all kind of handheld device that you have or whatever. I'm not talking about white waste. White waste is refrigerator, washing machine, some kind of thing. I'm talking about only e-waste, the handheld device or computers. We generate 12 million tons, and 80% of that is not processed. 80% of that just unorganized way, it just get dumped, and then it is landfilled without extracting the valuables. Now, why it is important for us? Why it is important for us? Why it is important for India? India is the third largest material user of the world. Third largest. After China, US, India. By 2030, the way we are progressing, GDP growth is about 6.7 or 7%. And population is very large, 1.4 billion. And we will be surely, shortly, by 2030, will be the second largest material user of the world. Where do we get that? You have a limited land source, you have 1.4 billion population, you want everybody to hold a laptop or a mobile phone, even every Indians, let's say at least 100, if not possible 100%, but about 60-70% people, we want them to give that possibility, and we give them a transportation advantage to move one place to another place faster, and so on and so forth. Everywhere you require material, you require minerals and materials, you require rare earth, you require more chemicals, you require more solar cells to generate electricity, and so on and so forth. So that ultimately our resources are restricted. So we are the first country need to circulate or have a circular economy. We need to reuse our all metals, we have to reuse our all chemicals, we have to reuse our all emissions, get the carbon from there, and so on and so forth. So that circular economy is all about that. Then only we need to sustain it. And otherwise we have to start importing, and we are importing today. Every handheld device that we are holding is imported from somewhere. And the most of the metals that is important is imported. The handheld device will be assembled here, but the important part of rare earth, which goes into semiconductor making, is imported. And you are importing and leaving it here and burying it in landfill. Instead of that, if you take the samarium, cobalt, or you take away gadolinium, or take away semiconductors, whatever is nickel, lanthanum, or dysprosium, europium, gallium, then you can, of course, extract it back, and you can manufacture it back, and then you can use it for your own use. And we don't need to pay extra money to import it. Of course, we are paying extra or more for importing that, which is much higher than the manufacturing cost in that country. So we have to be heavily dependent on circular economy, and of course the base metals, chemicals, everything. So we will talk about that more, and with this introduction, I would like to really all of you, all the chemical engineers, It's not about mathematics, physics, and chemistry. It's all about your vision and philosophy. How you do it, you need to, of course, learn, in the sense, read more and more books, and not only chemical engineering, but all sphere around. And of course, the direction that you are in. So don't think that it's only that this core courses or electric courses are important, but other things are also important. You should be good visualists. With this, I thank all of you and thank our own Chem Engg Association for inviting me for this lecture. Thank you.
Thank you so much, sir. And we now request our chief guest, Sri Robin Mukhopadhyay, to address the audience.
Thank you all. Good morning. And first of all, I was president Calcutta University Annual Association for organizing this very timely symposium, which without which we just cannot think of modern society going in its growth forward. So, respected dignitaries of the dais and respected seniors in the audience and our students, all young students here. I am very happy to be here, and I thank Calcutta University Alumni Association, Alumni Association for inviting me to give this talk, and I wish very good success for next 2 days of deliberation. And I know there will be many papers which will be presented during this period. So I just thought that I will just lay the basic ideas what chemical technology is doing in order to improve the sustainability in this society, particularly in the process industry. So as we know that sustainability is a topic of growing importance today in all aspects of organizational life. In fact, thanks to the ongoing and continued efforts by all the environmental bodies, the policymakers nowadays, they have taken a view that yes, it is a very important subject going forward, and new rules and new policies are coming so that the world remain much more sustainable than without this. Now, business and managers are increasingly considering ways to incorporate a balance among economic, ecological, social, and cultural value into their business models. At the same time, world is becoming exponentially more complex. So companies are facing pressure to reduce their environmental impact. However, the managerial tools and framework to bring sustainability into practice are still growing, and it is indeed their sustainability practices in a higher degree than the companies that adopt sustainability in a siloed way. So, therefore, there is a need to look into the subject in more holistic manner from company perspective. Now, keeping above in view, companies are getting more and more vigilant and duty bound to comply with sustainability deliverables. There are several different sophisticated and state-of-the-art technologies being employed in this area, and sustainability improvement in process industry are being pursued primarily. We know my previous speaker, Professor Basu, has already pointed out, basically to cut down the gaseous and liquid discharges from the industry. These are the main two areas that we are targeting. And with this background, I will try to just touch upon, because more and more will be talked in the next sessions. That is what I expect. I will just touch upon few of the chemical technologies, techniques that are being used in process industry, and in particularly refining and petrochemical industry, to make the processes much more sustainable. Now, in explaining these concepts, I am taking as example Petrochemicals, my company, and my company, just to give you few of the examples how the chemical technologies have been used to make the petrochemical process more sustainable from environmental point of view. Now, Haldia Petrochemicals, or HPL, as you know, it is one of the naphtha-based petrochemical complex, and it is the largest in Eastern India today. We are producing about 1 million ton of polymers total, polyethylene and polypropylene. The company is under management control of TCG, the Chem Group, and recently the Chem Group has also acquired Lamas Technology USA, which is the supplier of primarily many of the petrochemical technologies worldwide, and one of the primary technology provider for petrochemicals, including the cracker, naphtha cracker. Now, HPL actually produces, as I told you, the polymers like polyethylene and polypropylene, and chemicals like benzene and butadiene. Now, where all these chemical technologies has been used in make the process more sustainable in HPL, I will just touch upon. In a furnaces, we use all high efficiency and low NOx burners, which gives you the more fuel efficiency. As a result, your emission becomes less, and we do the maximize the fuel gas firing in all the furnaces, and there is no fuel oil firing in the cracker. Also, in the fuel gas that is generated, in 2010 when we went for an expansion of the project, we found that there is an imbalance of fuel gas generation. So we are producing more fuel gas than we need. So we made a scheme by rerouting that fuel gas to the power plant and running a GT, so that it gives energy and at the same time it does not burn in the uncontrolled way in the flare. So that way we are extracting energy and cutting down the fuel oil that would have been required for generating that much of power in the power plant. So these are the type of scheme that has been worked on. In the fugitive emission area, we use floating loop tanks. You know, or this use of these tanks where the seal is used so that the vapors are not escaped in the atmosphere. So that is another area of sustainable technology that we are using. And do not cut down on the fresh feed. So fresh feed means your capacity is going up and emission is directly linked with the capacity of the plant. So if I cut down the fresh feed and recycle more and more, and with recycle should be with value addition, that we need to think of. So new product has been developed, like from butadiene stream, we have taken out one more chemical, that is butene-1, and butene-1 we are producing from a recycle stream. And recently we have also planned few more recycle stream products, like benzene we are already producing, toluene and xylene, and hexane. These three products will be separated out from the through chemical process without adding any major emission from the process. Will be separating out from the recycled streams, and three more products will be producing, doing a value addition in the whole business, but at the same time not increasing the emission. We are also recycling the effluent water to minimize the effluent water discharge. So that is also another way of cutting down the water intake, reduction of water intake, and one step towards sustainability. And there is a green belt cover throughout the project, and for solid waste we are using incinerator so that it just doesn't go for rampant landfilling, which may affect your groundwater quality. So instead of doing that, we are doing the incineration of the solid waste. Now with that in background, in the existing HPL operation, recently we are planning one new project at Kadalur in Tamil Nadu. This place is a little off from Pondicherry towards south. So this place we have already taken the land and we have started site activities. Engineering is already completed, both basic engineering and detail engineering, and we are expecting that early next year, by mid of next year, we will be able to start the site work. Now in this project, we have gone for a unique technology, which you will understand that how the sustainability improved by that. This technology that we are using here is supplied by Chevron Laos Global, CNG. It is a crude to chemicals. Now in a crude to chemicals, we know that this is an conventional crude to chemicals already there is in practice in our country also. All the refineries that are having crude oil refining facilities, part of the product they are already converting to materials, polymers. So when you are converting the polymer to polymers, that part of hydrocarbon is not adding to the gaseous emission because we are not using it as fuel. So about 30% of the conventional refinery integrated with petrochemicals, it is converted to petrochemicals like polymers. And so 30% goes to material science, generating solid products, and 70% goes into the emission. Now in the crude to chemicals, there is no conventional distillation system as the refineries are using. It is directly crude oil getting converted to petrochemicals, the polymers and other chemicals. And more than that, the conversion of the crude oil to petrochemical is 70%. So 30% of conversion which was there in the earlier process, conventional process, that has been increased to 70% to petrochemicals, and as a result the emission emission has straightway come down from 70% to 30%. Because 30% is only used as fuel from this process and balance is going into the materials. In a emission, if you see from ton per ton basis, the conventional process emission has been cut down by 1/4 in the crude chemicals. Along with that, these are major technological improvements that has taken place, and recently few of these crude chemicals technologies are being used worldwide. We are not alone. South Korea, they are already under construction, one plant is there, and also in Middle East, Saudi Arabia, they are at Amiral, they are building one plant with the same process. So apart from that, in the same way, in the other technologies that we can talk of is the off gas that is coming out from the complex. These are all recycled to used as a fuel and not letting out in the flare system. So it is not getting the direct burning without generating energy. And the energy that is generated, that is cutting down the equivalent fuel that would have been used for this. Also, we are planning use of solar power in the new complex, which is a non-conventional energy that is being thought of now. The complex that we are building will be generating some solar power also, which will be used in the process. And in this complex, we will be doing the total recycling of the effluent. So it will be a zero liquid discharge complex. In HPL, we could not achieve so far zero liquid discharge in the existing operation. But the new project that we are planning, it is for the zero liquid discharge project that we will plan. And same way, use of incinerator here also we are planning. So like this, many of these chemical technologies are being used to make the process more sustainable while maintaining the growth. While on sustainability, I should also touch upon the plastic recyclability. And plastics are recycled in two forms actually. Either to use it in different shape and sizes, but as plastic because it has got prolonged life, so it can be recycled back. So plastics are getting collected. It is through extruder, it is making granules, and then again processed for producing new items. But at the same time, new process has come, and very recently I was going through one of the new items. ExxonMobil, they have already commissioned one of their facilities, which is recycling about 80 million pounds of plastics for producing back to hydrocarbon, which is used as fuel oil. And it can go to the refining system then. So this is the catalytic hydrogenation process that has been developed, and there are many other researches that are going on to develop this, and that will be the ultimate circular economy, where you are generating the plastics and then back to again hydrocarbon chain, where from you can start it afresh through a distillation process. So while the sustainability issue is looking at us in a big way, we are hopeful that the industry is also trying its best to meet the challenge, and I think going forward we'll see many more new technologies coming in this area. With that, I conclude, and I thank you once again for all of you. Thank you.
Thank you very much for the very enlightening speech, sir. Now our guest, Professor Ajit Kumar Dey, will make a vote of thanks.
Conveying vote of thanks is very conventional, but before going to that, I would like to announce one thing. One is one of our alumnus, Dr. Vishnu Pada Sen, actually late Vishnu Pada Sen, late Dr. Vishnu Pada Sen, he passed from our department in 1956. 1956. So he has written a book on a handbook on synthetic detergent. So that was published in the year 2004. Now, actually, he worked in Hindustan Liver Limited in 1970s and retired from there also, from Hindustan Liver. His wife, Mrs. Kipti Sen, she has donated this number of books, maybe 48 or 9 years. So that is given to our alumni association for the use of our alumni as well as students. So that is the declaration, the book. Now I would like to request Professor Raj to hand over a memento to our chief guest, Mr. Robin Mukherjee. Again, Professor Rai will hand over memento to our guest of honor, Professor Sanjay Sattva. Now I would like to convey sincere thanks to our head of the department for his what I can say unclaimed or what you can say unclaimed support. Whatever I told him, he actually maintained those things. So I convey sincere thanks to our education department. I convey sincere thanks to our alumni association, their executive committee members and general members, all our alumni, senior, junior, and particularly those alumni who are in the execution of this symposium. As Professor Rai told, we had a committee actually, but without any name basically, and within that committee, Mr. Sujit Kanti, he is from here, 1968. Professor Rai was there, Mr. Sujit Kanti was there, Dr. Saraswati Rai was there, and and basically myself and Vishnu was the secretary. So whatever this collection of this symposium papers, then the review of those papers, checking of plagiarism, all those sincere thanks to my departmental teachers, all the faculty members who helped in different ways, and particularly the students, and some teachers as well as the staff. Many staff they helped me a lot for basically the physical arrangement of this. I don't know whether you are aware of this or not. Whatever you are seeing this is actually we are telecasting this through video conferencing through Google Meet. So many of our alumni are there within this Google Meet. That's why you have even set up of laptops so that they can enter. Because one permission is required for entering into the system. So that is going on separately. Another is going on. We have a YouTube channel, Chem Engg. Through that YouTube channel, we are giving a live stream also from this hall. So all the arrangements that has been made by one of our staff, Mr. Vijay Bhavar, as well as many of our students, So I want to say thanks to them all. And for the students also, we are not able to conduct our regular alumni meet, or you can say reunion, which was due during last year, but we couldn't able to conduct those things due to COVID. So this year, many of them are telling it's a reunion, but we are trying to convince them that this is not reunion, basically it's a symposium for 3 days. But definitely, there will be a felicitation program on the 3rd day for the batch of 1994, 95, 96, and 97. So they have passed 25 years from this department. So they will be here on that days also. So it's quite a mini reunion, and as you see, they are actually enjoying, our students, they are enjoying a lot. Already they have played a lot of games, I think football, cricket, badminton, chess, like this. They already have played all these games, and they have given some painting works also here. So it's a lifetime remembrance that they will remember that they did something in their department during their ongoing educational process. So I want to say thanks to them also. And I convey thanks to Professor Symposium-2022. He is also our alumnus, and he also helped a lot for organizing this, particularly sponsoring this program, this event, in 2 ways. One is the direct sponsorship, and another is by sending some advertisement materials. So thanks and regards to Symposium. And I always sincere thanks to Mr. Robin Mukhopadhyay. He is the Vice President of India Petrochemicals Limited. And actually, what we know, he is actually looking after the project which is coming in Tamil Nadu. And when myself and Professor I met Mr. Subhash Chatterjee in the Vice Chairman of APS, he given us some hints that they are going to install a new petrochemical industry in Tamil Nadu. And what Mr. Mukhopadhyay has not told you that plant is a very big plant. What he told that it is nearly 3.5 times larger, 3.5 times bigger than what is there in India. So what they are doing, actually they have 2 parts. One is they will be importing crude oil from abroad. So that's a part from crude oil to naphtha or this type of product here. Then from naphtha to petrochemicals. So I would like to these experts for giving some technical talks to our students also, so that they can understand what is going on, because it's a combination of both the process. So there may be some synergistic effect also there, but what Mr. Mukhopadhyay told that they are actually trying to reduce the carbon footprint. So they are synchronizing these two processes in such a way that there will be more and more recycling to get valuable recovery of the product, as well as efficient use of fuel. So I think we will be able to get more and more idea how these are going on. This will be going on better, you can say. So thank you, Mr. Mukhopadhyay, for coming here and giving a talk on the subject of sustainable development, particularly this recycling part of the petrochemical products. So by this, I would like to conclude this inaugural session. Thank you. And next, I think without any break, we will start the next session because we are late already. So we will start the next session. And Professor Parvashar Dey is the president of our Level Association. He will take the chair of this session. And there are three lectures in this session. One is Professor Symposium-2022, who will deliver a lecture for Israel. Another is Mr. Devjit Chandra from Dock Chemicals. He will deliver a lecture. Actually, Devjit also is a student of this building. He is from Chemical Technology Department. So he will give a talk. He will give us a talk on their products and what they are doing. And the last is from IOCL, Dr. Taupam Beda. He will also deliver a talk on the subject. So we are concluding this session here, and immediately we will start the next session. Thank you very much.
Thank you so much, sir, and thank you to all the dignitaries present here, and particularly thanks to Mrs. Kirti.
Silence please. Let me start the next session that has been announced by Austin Group. This is the sponsored lecture session. We have three speakers, Professor Sudhosanta Basu, Jagdish Chandra, and Dr. Tapan Bera. I would request all of them to come on the dais. Sudhosanta, Jagdish, and Tapan. Before I go on taking the lead, on behalf of the organizers, let me convey our gratitude and thanks to the organizations like CPAR, IOC R&D, Holger Petrochemicals, Dot Ketal Chemicals, and TPP Hong Kong Limited. Without their financial support, this program would not have been organized in the way you are now seeing. So with this, it is the sponsored lecture as has been pointed out in the program. The first lecture will be delivered by Professor Sudhosanta Basu, and introduction of the Basu has been made by a matter of. Here I like to mention that Sudhosanta Basu, completing his BTech from this department, he did his PhD from IISc Bangalore. Prior to taking over as the director of CSIR, IIMMT, that is Institute of Mineral and Mining Technology, Bhubaneswar, he was professor and head of the Department of Chemical Engineering at IIT Delhi. You are also the Associate Dean R&D of the same institute. You are Director of Central Institute of Mining and Fuel Research Institute, SIMPA. He has vast work experience on development of materials for energy conversion and storage devices, magnetic materials, waste technologies for circular economy. He has published more than 240 articles in high impact journals with H index 42. He has in his credit 15 patents and 2 technologies transferred to various industries. He is a fellow of National Academy of Science of India. He is also the fellow of National Academy of Engineering, Royal Society of Chemistry, UK. He received RDI Award, Dr. A. B. Ramarao Foundation Research gold medal, MSRI medal. He is listed among top 2% of most scientists of world by the Stanford University in 2022. He is editor, associate editor in editorial board of so many international journals like Wiley, Springer, Oxford Press, ACS, and Taylor Transit. With this limited information, I will invite Professor Sudhir Basu to deliver his lecture. Professor Basu, please. বাচ্চা কাচ্চাগুলোকে ভেতরে ঢুকতে বলবি তোরা একটু, না আমি যাবো, সব বাইরে আড্ডা মারছে। বিশ্বজিৎকে ধরে আন, তাহলে সব চলে আসবে।
you understand that this is a linear economy, which you all know, which we are all part of it. You have raw material, you produce it, you consume it, you waste it, which goes mostly landfilling, and some processing is done. What about circular economy is saying as that, but when you make the waste material, you then go through a process by which you get your raw material back, which was I was talking about. So you have, let's say, handheld device, electronic device, or mobile phone. So you repapper, take the lithium-ion battery, takes the lithium back, take cobalt back, which is very costly, not available. You take the semiconductor device, take your gallium, lanthanum out, and use in semiconductor making. You take your plastics out and recycle the plastic. So this is the process that you use, that you take the waste, recover the important raw material, and put back into the system. So that's how the circular economy works. And this is how you need to develop this, that it goes through a process by which you get back your original material. In the process, you can also probably generate a lot of water or chemicals, and will generate a lot of waste or solid waste, but you need to reuse them as well. So water, zero discharge plant, so water needs to be reused after refining water. So that's a part of circular economy. And so there are two concepts. One is that you have an existing economy. In that, how you can set this up. That is one concept, which is difficult because already you know how refinery works, how petrochemical works, or how a metal industry works. So it was meant not for circular economy, it was meant for linear economy. Now you need to introduce, whether it fits or not, I'm going to look into it. Other one is to change your technology and bring circularity in your design, that circularity in your process, so that it becomes a circular part of circular economy. You understand, I'm sure at this point, that by design of plastic, I should design a plastic such that it is recyclable. All plastics are not recyclable. Okay? So I need to design a plastic which is recyclable. I need to have a process where the circular economy will fit it. So that is what, and there is ample scope in automobile, which we do it, already we do it in our country. The automobile engines, after the end of the life, many times used in agricultural industry to run a small device which will tilt the soil. It is done, but it's kind of done in a jugaad way, not in an organized way. You go to the many farmland, you will see that they're using an old Honda, maybe two-wheeler single stroke, now of course is four-stroke engines, taken that part and use it for tilling of the soil. Okay, so those are being done, as I said in the morning, and we of course need to do it in an organized way. So automobile industry, all the scrap, we need to recycle it to make a good steel. Food industry is, again, it is possible to recycle back whatever you have taken out from the soil and agricultural product. Chemical industry, metallurgical industry, I will give much example today on metallurgical and chemical industry, wastewater and emission management. Wastewater, I don't need to explain, you all know, emission is CO2. You cannot let your CO2 out, you have to store it, sequester it, store it, and utilize it, convert it to C1, C2, C3 chemicals or platform chemicals. Platform chemicals are like formaldehyde, formic acid, methanol, ethanol, and after that you can, anything you want to make, you can make it C4, C5, C6, you can make. So coming back to the current mineral sectors, there is a good, after COVID, there is a good rise in the metal index all around, and you can see that positive growth of 18%. This is, I'm talking about the mineral sector or metal sector. There's a positive growth in 21-22 in mineral sector, which is 18%, which is a huge growth we have seen in India. So there's a huge scope to, use more and more minerals and make more metals. Huge scope in the sense there is a demand in the market. Otherwise, there will be no growth, right? So where this demand is there, where the minerals will come from, you have to have your own minerals. You have to, of course, use it, or you have a low grade ores, or you have to recycle your metal to have that growth plan. So there is a depletion of high grade ores, then there is additional cost of beneficiation. Because you are using low grade ores, then you have a higher cost of because of the beneficiation. When you refine your ore from, let's say, about 40% iron to about 60 or 80% iron, it goes to the blast furnace. So that is become costly. And all these others, I am just giving all the other like bulk quantity of industrial waste that is generated. You can reuse it in your in the opportunities that you have, the goal that you have. Now I'm going to show you the waste that we generate. You just look at this diagram. Almost equal waste is generated in minerals and metals is 28%, correct? Fly ash and bottom ash about 25%. The total waste that we generate in India, and agricultural waste is about 32%, and others is mentioned rest of it. So three waste is mainly there: mineral, metal, fly ash, bottom ash, and agricultural waste. So why should we not valorize these waste and get a product from there? Let's say I have rice husk or wheat husk. Can I get silica out of it? And silica is a very important product in refractories. Why should we waste it? Okay, why should we burn it? And so on and so forth. There are many things that you can, and you can do it. Now, I just want to emphasize in the mineral metal sector, there are a lot of slimes. This is the red mud point, which is in aluminium sector, which is generated or called bauxite residue. There are many other ways, like if you generate 1 ton of steel, you generate at least 0.6 tons of waste. If you generate 1 ton of alumina, not even alumina, 1 ton, you generate about 1.2 ton of red mud, which is also called bauxite residue. Red mud, which I am showing you here. So just think of it. To produce 1 ton of steel, I am generating 0.6 ton of all fine slimes, gang material. While I do beneficiation, then I get a slag in blast furnace or lift half furnace, and so on and so forth. So there is, you cannot just let it go or you cannot store it. There is also health hazard, environmental hazard. Now I am showing an integrated steel plant. Where are the points where there is a lot of waste is generated? The process of making steel is shown here. Those who are not in this background, but more or less you must have studied industrial chemistry or in your practice in chemical technology. So you have coal, you have iron ore, you have limestone that goes to the blast furnace. The blast furnace of gas, which will give you dust or blast furnace flue gas, which contains about 20 or 30% of iron. If you go to the SMS, which is a steel melting shop, which will give you the SMS slag, which contains 70 to 170 kg per ton of crude steel generated, will have that iron line. Then your coke breeze also will have iron. So the coke breeze will come up from coke oven and then hot blast furnace. And the blast furnace slag and all of these basic oxygen refiner slag, all of these will have a lot of material that is coming out, and you need to just mention how much iron is there per ton of steel generated in the different sectors or different effluent that is coming out of integrated steel plant. So you should tap them. So there is all these, the red mud and all these slimes, fine slag, mill scale that I showed would have an environmental effect, would go to the land, water, air. Sometimes they are toxic, containing lead, and many others. And so we need to, why don't we take out the iron and then landfill it the way that all the impure material or the material like lead and everything is taken away. So the mantra is to have 6R: reduce, reuse, recycle, recover, and resource. Because whatever you recover is a resource for you. So that is what you should should do it the way that we all want that this planet to survive millions of years, not few thousand years, because we do not want to mine more and more and use our resources and then generate so much of waste material and also poison material, which is not good for human health. So a blast furnace flue dust, which I was talking about, two different steel plant that we were working on, Tata Steel and Rourkela steel plant, which have this kind of material, which is iron oxide about 51%, okay, which is good amount of iron oxide. Then SMS sludge, also that steel meal, also would have a good quantity of iron oxide. So what we did, we have a beneficiation process which is a thermal beneficiation. Normal beneficiation uses a lot of water, and then it goes through spiral. You must have learned in unit operations. It goes through a bobbing column. It goes through a screen and many other processes by which you separate the gangue material and then concentrate your iron or concentrate to any other mineral that we talked about. We took this material which is already concentrated about 50% of iron, 60% iron, 45% iron, and gone through a reduction roasting route which we are showing you here. And it can not only take the slimes or the low grade iron ore or banded iron ore, also takes those SMS sludge. You can do it, and you can thermally beneficiate it by a reduction roasting process in a kiln, and then you do a magnetic separation, and then you get your iron, concentrated iron. You can also use the PF SMS dust, and we are showing you here that how you can sinter it, make pellet, and you can make briquette and charge it to blast furnace. And many other things that we have already worked on. So on blast furnace, SMS dust and sludge, we have given it this Techno Environmental Service Limited, which is working on Bokaro. We have already given our technology to microproject and briquette plant to get it from the SMS sludge. So how they can make briquette, and this briquette can be charged into blast furnace. So that means we are trying to reuse all the wastes or getting the value out of waste that is generated in making of steel otherwise. Okay, so these are the shown you here that magnetite or coke mines, what the process we do, or magnetite material, what we do here. This is more about the same process in a little elaborate form. Those who are interested, like it gives you an extra yield, increase weight of the iron ore, and easy transportation, no tailing pond because it's just a thermal beneficiation, so nothing will be generated, no water is used. And this is the process, and this whole thing which also have 35 to 55% iron can be used to 60% and can be fed to the blast furnace or electric arc furnace to make steel out of that. Then from the steel, I want to go to the non-ferrous sector, which is waste valorization that I am showing you is some 3 examples. First example is using a membrane technology and electrolysis method to, in your effluent, many of the effluent will contain sodium sulfate bearing effluent, sodium sulfate, sodium bisulfate. So what we did, we have a 1 meter square of cell, and where we apply potential, and it goes through an electrolysis process by which we can get back to a caustic and get back to acid. That means a sodium sulfate and sodium bisulfate in the effluent, which is many effluent would have that, especially this effluent will be there in nuclear power plant. And for heavy water board, we have given this technology that using electrolysis, after this is one single cell is shown you in 1 meter square, but many cells together stack, which can generate caustic and acid. So sodium sulfate is applied, of course electricity, that is a cost. The electricity can come from renewable source or photovoltaic, and that can do it. So then we also generated pure metal from spent catalyst or alloy scrap, sludges and secondaries, and we have given a technology called Rumapid for making cobalt, and then we have given a high pure tellurium powder from anode slime, which is coming from alumina industry. This is a non-ferrous industry, one example of beneficiation of chromite ore, Odisha has a lot of chromite ore and chromite overburden. Even we were running a pilot plant in our premise of 2 tons per day on making nickel from the chromite overburden. But this we are showing that why you want to make chrome metal, and you generate a lot of this, all these tailings are generated in chrome metals and still contain good amount of chrome, of chromium oxide, a chrome metal which is required in iron, chromium, steel making. Chrome itself is used in the market for coating and electrolysis process. So it generates in all the points that I showed you here, taking 1, taking 2 and 3. Okay, generates a lot of effluent which contains chrome, and so we have a process to get chrome back from the effluent and reuse it. Not only that, we gave this cobalt metal from super alloys, scrap and sludge. Cobalt, there is no source of cobalt in India. There is no mine. There is no minerals of cobalt available in India. The only source is the scrap. And so for the cobalt alloy scrap, which is already bought from other countries, or sludge, we have found out a way to make cobalt metal using a hydrometallurgy route by solvent extraction and then electrowinning. So the electrolytic cell, solvent extraction, leaching, solvent extraction, electrical cells, and then this we have given a technology to Govind in Rajasthan. This technology is further they have taken to Africa because there were big mines in Africa. So these are the things that we have already done, and all from the waste. The process flow sheet from cobalt is shown in here, and the cost part is also shown in here, and all the process that it goes through: impurity removal, solid waste separation, then hydroxide precipitation, cake leaching, and solvent extraction in electrowinning. This is the chromite overburden that we talked about. Nickel, there is no nickel source in India. Why do you get the nickel? Nickel is coming mostly from abroad. So nickel source, the chromite overburden is containing nickel. That's the only source of nickel we have, and we have a hydrometallurgy plant to get nickel from chromite overburden. Now a little bit more of the critical minerals, very important for India. The critical minerals goes into your all electronic devices. Critical minerals all goes into your electric mobility. All electric mobility got electric motors containing magnet. It contains neodymium, iron boron magnet. Okay, NdFeB magnet, neodymium, iron boron. Neodymium is a rare earth which is not available in large quantity. It's there in deep sand in Odisha, Tamil Nadu, and all the coastal area, which is called monazite, which also contains thorium and uranium. So once you take out the thorium uranium, which is part of the atomic mineral division work, it is now available in the market in terms of concentrated lanthanum, gallium, and neodymium. But you have to make pure 10.99% of neodymium to make NdFeB magnet, which goes into the electric motors, and that is how the electric mobility works. All these magnet comes from, or electric motors come from China. Tomorrow China says, I'm not going to give it already, we have a geopolitical situation with China. So then you have it, where is electric mobility of 1 billion cars by 2030 running on electric motors or electric power will happen. This will not happen unless you resource your own rare earth. Well, not only in this, there are semiconductor devices that also have a lot of rare earth. Your CFL bulb will have gallium nitride, gallium is also a rare earth, so on and so forth. So the circular economy of rare earth is so important that the process that I have shown you is cumbersome. One is to have mining process, okay, from primary sources, which we have little, not much, but we are the 6th rare earth depositors of the country in terms of rare earth deposits. We are 6th in the line along with China. US doesn't have rare earth, but still they have the holding all that they get it from other countries. They are in Africa, in Australia, in China, in Russia, and India, Vietnam, and some in Myanmar and in Russia, and India. India comes 6th. In terms of deposit, they come 6th. In terms of making, we are far behind. We don't make pure metals of rare earth. Indian rare earth, of course, makes it, but they make most of it. Their work is to feed the nuclear fuel to the NPC nuclear power corporation. But they make a lot of oxides. Oxide is available, but make ND49, make gadolinium, samarium cobalt is also a magnet, okay, which is also being used. Your car will have about thousands of magnets. Any car will have thousands of magnets in sensors and actuators, or the car doors get locked. All these are lots of sensors and actuators, and those are all magnet-based sensors and actuators. I mean, your own, not the electric cars, but I'm talking about the IC engine cars. So there's a lot of requirement. So the way we do it is, you can mine it, you can process it, but you require recollection and recovery back into the system in the economy. That is what we are talking about, and that's how we have to go for rare. And this is also part of circular economy. That's why I'm showing you. And the economics, social, and environment, these are all regulatory regulations and awareness and business model that is already existing in other countries. And we need to do it very big way in India. Because in our country, mobile phones are not being, of course, now the legislation is coming up that Samsung can sell mobile phone only after it takes back a mobile phone from you. Okay, he cannot sell just like that. That regulation already has come, and it will be 2023. We'll see that regulation is coming up with all mobile phones and handheld devices. Similarly, business-wise also it will work well for the automobile companies to recycle the magnets, that electric motors that will be generating so many electric vehicles, 1 million electric vehicles running by 2030 in India, and we generate so much of waste. Every year when you scrap a vehicle after 10 years or 15 years or 5 years, okay? So the other sector that we are talking about is the bauxite residue, which I talked about, and this is bauxite residue. There is a big fallout because it's alkaline in nature, so it makes your soil alkaline. So you cannot use wherever you are putting your red mud or bauxite residue, dumping it, and then it will leach slowly to the mainstream or to the other areas. So soil contamination, groundwater pollution, these are fine particles goes into the atmosphere, and many other problems are there with the red mud or bauxite residue. So we have come up with a technology on this, and just showing you that red mud is generated 8.8 to 1.5 ton. Red mud is 8.5 ton on aluminum. Okay, so a large amount. Alkaline is very, very high. So and there is a submicron size particle. So and they also contain red mud. If you see, it has contained about 20% of iron, 10 to 20% of aluminum. Aluminum is very costly material, by the way. It contains titanium. Titanium is another source that we do not have except for the beach sand, where the titanium is there. And titanium is used not only in pigment but also in alloy making. And calcium oxide, silica, and sodium, which are a very small quantity, have no use. But you can take out iron, you can take out aluminum, you can take out titanium, which is big. We all titanium, 90% of titanium requirement of India is being imported. Only 10% is being made in Kerala. And so there is a big requirement of titanium, and if you want to make aerospace industry, there is a big aerospace industry, big requirement of titanium. The titanium source only will come from somewhere else. And so we can do bauxite residue, we can do thermal treatment, magnetic extraction, iron recovery, and fibers, and then aluminum recovery, and then you can get the rare. So we are working with 3 companies, CSI NML, the National Metallurgical Lab, IMMT, where I am coming from, Institute of Minerals and Metals Technology, JNRTC, this is an aluminum research lab in Nagpur, Jawaharlal Nehru Advanced Research Lab, NALCO, Hindalco, and Vedanta. These are the 3 companies you already know, aluminum companies. NALCO, Hindalco, and Vedanta. All 6 of us are working together. We already showed in a lab scale, bench scale that it works. Now we are working on pilot scale. All 6 of us together. We put our own money. We have not gone there to get money. I put my own money from my own reserve fund. They have put their own money, and we are all working together to 100 kg scale to show that red mud, we can utilize all the important material that I showed, plus the rare earth that is there. A big amount of scandium is there. on this. I'm not going to give you the paucity of time. So you have got the total project is 6.5 crore, and each one has to put about 2 crore each. Okay, and then the fly ash, the valorization of fly ash, which is also waste. And you can get your calcium silicate, you can get your quartz, you can get iron oxide, and this iron oxide contains iron. Okay, so that's how you can get your silica quartz, which we mainly see here as glass material. You can get your calcium silicate, which we use for in fire retardant layer in houses and in halls that we use, and aluminum, which is very costly, and get your there. And this is the process. You go through a leaching, sulfation, roasting, separation, and precipitation, and so on and so forth. So this thing, it contains scandium about 111 ppm. You can bring down to about 700 ppm concentration. Uranium contains about 466 ppm in fly ash after recovery of iron. So, and these are very important, as I was saying. E-waste, there are devices. I was talking about this. A battery, lithium is not there in India. You can get magnets. Magnets is there in e-waste. Lot of magnets. You have optoelectronic device like CFL, which contains a lot of gallium nitride, and magnets is this. So you have to get back all of this material by going through spent LIB. So you have electric mobility. Your cars will have huge number of batteries. Your mobile phone and your laptop will give a lot of batteries every year. And see, millions of batteries that is being generated. So it is expected by about 2050 that about 25 million batteries will be waste generated in India alone, in 25 million tons. Okay, and so this is of course projected, but right now we are generating around 6 to 7 million tons. So that is what we need to do is lithium-ion battery. We can have a direct recycling to a lower from car. It can go to the electric sector, backup power, or we can do hydrometallurgy, do pyrometallurgy to get back your material. So this is how you do leaching, you do separation, purification, pre-treatment, of course dismantling, and then leaching process and separation, purification to get back your the cobalt, get back your lithium, and then you can reuse them to making batteries. So these are the hydrometallurgy. There are pyrometallurgy route. All is not good because you are actually using a lot of energy, plus you have a lot of emission just by heating them in the furnace. You have pyrometallurgy, which is a mixing of hydrometallurgy and pyrometallurgy, and completely hydrometallurgy, which is of course environmentally very good process. You don't generate much less waste from here. So there are companies like Accurate, Green, S Green. They're all working here in India, as well as the E-Parisara in Bangalore. There are many other Indian companies are all working, but we do not have the plan to generate or collection system is not there in place. We require a big collection system. Many of them are not collected. So what we did 10 years back, we worked for Nissan. Nissan had an electric vehicle plan for the last 20 years. 10 years back, they came to us on their own and with the interpreter and told that this is a Nissan battery and we want to get the valuable back. And we were working, we were very well known worldwide for our non-ferrous metallurgy and non-ferrous extraction, which is electroweighing, hydropyrometallurgy and hydrometallurgy. So they gave them the technology. No one talked about it 10 years back. Now people are talking about it, and we gave them technology and they must be using it. We don't know because we did not patent because they was not allowed to patent because they take it back part and parcel everything. Whatever they brought, we did that and they took it out everything and technology is given to them and we get back all the element. We get a lithium, cobalt, aluminum, manganese, nickel, copper and fluoride. Of course, this is there for binder. So all these we required for them for the Nissan battery that we worked on. Today, of course, there are other R&D processes we have worked on, which is mostly on solvent extraction processes, much more green technology than what we gave to Nissan, because that we cannot give to anybody else. We are bound by our contract. Okay, so we developed this technology, and the recovery is shown you here. And finally, we have to also do our self-design. Lithium-ion battery cell design have that it is recyclable. This is something on spent magnet. we get NaPi magnet, samarium cobalt magnet, we get cobalt oxide and samarium. So samarium oxide, we do leaching, precipitation, solvent extraction, stripping, and then calcination to get back a material. So this is the process. You take the scrap magnet, you do leach, this is leach decker, then you are stripping, raffinate, then you get all your oxides, and then you give the product that can be reused to make samarium cobalt magnet, NaPi magnet. So finally, I end up here that I just talked about that structured approach is needed to minimize waste generation, because you have your process to be such that you generate less and less waste. We should use reduce the generation of waste to the advanced technology. Okay, improvement technology, bring circular economy makes sense with R6 that I talked about. Okay, R&D activities in industry should be emphasized to enhance the synergistic effect. In the sense that one hand you need to generate more and more, because we have a 1.4 billion population, you have to cater to them everything. In another way, you have to resource material, and other direction you have to, of course, process your waste. You just cannot go for landfill. So that is what is need to work on, and waste to be treated as a secondary source, and complete valorization is possible. Hardly anything goes to the landfill. Complete valorization is possible if you really work on it, and these are economically viable, we have already shown. So today's tagline is today's waste is tomorrow's wealth. Thank you.
Thank you, Professor Basu, for your lively presentation. I am constrained to allow you to have any question towards Professor Basu, as the time is limited. So let me finish this session, then I will allow perhaps some questions to the speaker. Now I like to invite Devjit Chandra. He completed his BTech degree from the Chemical Technology Department of this building. After completing, now he has acquired 50 years of experience in refinery and petrochemical application. He has worked in India as well as in the Middle East. He was in technical sales and service role and has been associated with multiple refineries and petrochemicals in India and Middle East. His work area includes the world's largest refinery and of gas cracker. He has been working in the technical service role in Dow Chemical Limited for the last 1 year and supporting Asia Pacific and Europe in terms of service compliance, continuous improvement, and technical recommendation for delivering value addition. The area of expertise includes implementing chemical programs targeted to meet customers as key business driver in order to improve asset reliability, profitability, and sustainability. Before I invite Devji, Samuel, do you like to share the dais? I heard that you like to share the dais during the lecture. Okay, thank you. So, Devji, please start your lecture. this happening staff obviously that come out. So I will ask that to sit down for a couple of minutes before he comes. I am in hurry, so I would invite the next speaker. If you do not mind, I think. Dr. Topan Bera. He is from IOCL R&D. Working there as Deputy General Manager in R&D sector of IOC, India's largest commercial undertaking. His current responsibilities include creation and operation of hydrogen production, storage and dispensing infrastructure, hydrogen production and storage facilities, HCNG process, commercialization, etc. Dr. Bera received his degree, of course, from this department and entered degree from IIT Kharagpur, I think. PhD from Belgium. He has published 8 articles in high impact factor journal. He has in his credit 5 patents and 16 conference proceedings. Dr. Bera is winner of American Institute of Chemical Engineers Travel Award 2011 from its catalysis and Jackson Engineering Division. He is member of Hydrogen Association of India. We are going 2 months. I would request Dr. Bera to start.
Good afternoon, everybody. It's master day to stand on the dais after so many years and speak in front of professors who are teaching chemical engineering when I was a student here. So I know the things that I was working. So I'll speak and we are running late. I'll not take much of your time. I'll speak on hydrogen. Initiatives of Indian R&D. So in earlier lecture, Professor Basu has shown UN Sustainable Development Goals actually, and there 13 point was the climate action. So we need to control the temperature of the Earth, Mother Earth, below one means between 1.5 degree with respect to pre-industrial air temperature. So that we can the art which is borrowed from our elders, we could keep it for our juniors also. So our duty, responsibility is to transfer the art to our juniors. So with that background, I will say it's time for hydrogen. Although Indian Oil is oil and gas company, and the product we sell, it produces a lot of carbon dioxide, which is increasing day by day. So now we are talking about carbon-less fuel actually, and we are working on that. Earlier on, there are many ways on hydrogen, but all leaves out with time because the economics of that. But after COP26, when our Honorable Prime Minister declared the Panchamrita goal, where you need to achieve net zero emissions by 2070. By 2070. So there, I think future of hydrogen is very large. So with that background, I would say this is a general slide. So it has, as proved, as limited layers. And so there is a sustainability issue, it's a sustainability symposium. Then there are global unstability like Ukraine war, which leads to fluctuating food price, and which leads to and also their environmental concern. So with these challenges, market forces, change is always happening, and we reach to the age of Homo sapiens after many changes. So although we are continuing to many years, carbon but we need to slowly move to carbon-less fuel. So this is what India is doing actually. We are importing almost 80% of the crude and 50% of the gases. So a lot of dollars we are spending for importing crude. So now we need our own fuel, and where hydrogen may play an important role. So sustainable energy is the solution. So look what is hydrogen actually. So if you see, hydrogen is the most abundant element, but we never get it elemental form. It is in the compound actually. We need to extract hydrogen by many processes, when like methane reforming or utilizing many things. And if you see the journey of the fuel actually, we are slowly moving from coal to oil to natural gas to hydrogen actually. So carbon fuel. So hydrogen is a sustainable solution for meeting stringent environmental norms in future and mitigating the climatic change. So look, here is the drivers. What are the drivers? Earlier there were many ways for hydrogen, but now environment government is talking about environment and the technology is available. Environment with respect to carbon dioxide emission, India is emitting about 2.5 gigaton of carbon dioxide, which is 7.3% of the world, which is, although it is less, per capita emission is less, but it is considerable. And if you see our capital's air quality index, it is 15 times poorer than the food recommendations. So those are the environmental concern. Then the technology part, we have many. Now we have the CCS technology. Moreover, the cost of the renewable energy has come down. It is almost 4 cents per unit actually. So the technology are available. So it is the right time to seek out to hydrogen actually. And hydrogen is a chemical, can be stored like in oil or gas. So with that background, I will talk about a little bit on hydrogen production technologies, then hydrogen used in mobility sector, then what Indian Oil is doing to commercialize hydrogen, and then its storage part. So this is general slide I will speak actually. Let's talk about the color of the hydrogen. People are talking about green hydrogen nowadays. So there are many colors. I have listed few of them. They are grey hydrogen, blue hydrogen, green hydrogen, turquoise hydrogen, and yellow hydrogen. So grey hydrogen which we normally obtain from natural gas chemical reforming. So we emit carbon dioxide to the environment. We get hydrogen, but we emit carbon dioxide. So that is why it is called grey hydrogen. And brown hydrogen is the hydrogen which when we get hydrogen from coal by gasification technologies. So, but this process is very simple, but emit lots of carbon dioxide. So what we believe that this grey hydrogen can be facilitated to develop the hydrogen market. Then we need to move to blue hydrogen, where you can capture the carbon dioxide by CCS technology. So you can produce hydrogen from a carbonaceous material, but you need to capture the hydrogen, capture the carbon dioxide, and then use the hydrogen. Then your emission will be less. Then green hydrogen, where instead of you can break water to get hydrogen by electrolysis process or any other high temperature process. But there the electricity should be the renewable electricity like solar or wind electricity. And we also believe like biomass based hydrogen is also a green hydrogen, because if you see the life cycle analysis of biomass, you can consider a green hydrogen. Then turquoise hydrogen, it is in the research level where you can break methane and get hydrogen, and carbon will be obtained as carbon actually. So, but there is no commercial technology available right now as far as my knowledge. Then nuclear, you can use nuclear power to get hydrogen, which is yellow hydrogen. So that's the color. Let's concentrate on, we are talking about blue hydrogen and green hydrogen right now. So these are the process, I think you all know actually. Steam methane reforming, partial oxidation of natural gas and technologies by which you can produce hydrogen from a fossil fuel like crude or naphtha. Then splitting of water using electrolysis technologies. There are many electrolysis technologies like protonation movement technology, alkaline technology, solid oxide electrolysis technology. But they have all pros and cons. But all technologies are available except SOEC technology, which it is at the research level. But there you can use the green electricity also. But renewable hydrogen oil, the green hydrogen is then when you use the renewable power like solar or wind power. Look, hydrogen can be produced at lower cost, but when the consumer get hydrogen it is at higher cost because it is a big value chain actually. You produce hydrogen, then you purify it because for hydrogen using an IC engine, normal engine, it is not efficient. So you have to use in a fuel cell where you need 99.99% purity. So purification is important in compression, bottling and delivery. Because of this big value chain, the cost of hydrogen is, when a customer buys hydrogen is higher actually. But our refinery produce it hydrogen at 100 rupees kg, but when we buy hydrogen, it is almost 800 to 1000 rupees kg. So here I will say, show what Indian Oil is working with ISC Bangalore. This is a biomass gasification technology, oxy biomass gasification. So there we have proof of concept has been established. We can produce 100 grams of hydrogen per kg of biomass. It has been demonstrated. Then we have purified that hydrogen to 99.29% purity. There are many components, but you gasify the biomass. Then that gas has been used in a plain fuel cell, and we have checked the performance that it is not deteriorating. So we are able to demonstrate that oxy-steam biomass gasification technology can produce hydrogen which is suitable for fuel cell technology. And we are going to demonstrate it, bigger plan in our R&D second campus actually. It's about 10 kg per hour, then we will go for the commercial stage. This is one integrated gasification, coal gasification actually. And I think Dr. Basu was saying on many processes. Here actually, instead of producing, not only the technologies are available for coal which is not suitable for India, because Indian coal has 5 years coal. And they are suitable for, they not only work in entertainment gasifier which is higher temperature slag is formed. So they are here, we have a multi-feed gasifier technology we have patented actually, where you can handle high gas coal with low reactivity Indian coal along with petcoke which is a low reactivity. So what we do is a two-step process. First stage is the low temperature gasifier, where it is a movement gasifier, but ash is removed and then the same gas which is produced goes to a second gasifier along with the petcoke or fertilizer oil, which is the entrained reactor plasma gasifier, where you can reach higher temperature in 1400 degrees centigrade and you get hydrogen. It's a patented process and we are working with simple Gamla to demonstrate technology at their site because coal is available at their site. Then this is a little bit of literature search on water electrolysis. So as I said, you will know everything what chemists did. There is a electrode, there are electrode cathode anodes, and there are different technology. Alkaline technology is there because they changes the electrolyte. In alkaline technology, you use KOH. In PAIL, you use naphthalene membrane, and solid oxide is the new technology, and it is in the research stage actually, where they say the efficiency of the electrolyzer is higher, like you can reach 70% or 80% compared to alkaline or plain electrolyzer, where efficiency is 40 to 50%. So this is a literature review. This is the cost economics actually. If you look, still hydrogen produced from a SMR is cheaper actually. $1.5 almost one, which is very cheap. But there the hydrogen is the either grey hydrogen or if you capture it is a blue hydrogen. And it can be produced centrally in a refinery or a fertilizer plant. But when it reaches to the customer, the cost goes up. So if you see the electrolysis process, where the cost cheaper in the sense that you can produce hydrogen locally and dispense it. So still it will be cheaper compared to the hydrogen if it is transported from other places. And if we get the natural gas network, hydrogen network is not there. So that is why its cost is going up. So if the network, if we use the natural gas network to transport hydrogen, maybe the cost will come down, and we are working on that also. So this is the economics, and this is the demand charge actually of global. So if you see by 2020, one is using 90 million metric ton of hydrogen, and it is going, the average growth rate is more than 7%, and it is expected by 2050 it will be 500 million ton hydrogen. So there is a huge market of hydrogen, and so which can improve the environment and which is good for sustainability also. This is world, and then India, if you see the Indian market, we produce 6.8 MMTPA of hydrogen, and we 6.7 MMTPA of hydrogen. Okay. So we have a little bit of surplus hydrogen in the fertilizer industry and the refinery industry, which we are planning to sell as a blue hydrogen. So this is the Indian market. Then let's see the application. So hydrogen can be used in a mobility sector. You can blend hydrogen with CNG, which is called hydrogen blended CNG. Then hydrogen can be used in ICNG or FC fuel cell buses. So this is a pilot plant which we did under the direction of Honorable Supreme Court, where we 50 buses in Delhi was running for 6 months in 2020 with hydrogen blended CNG, and we observed the 70% reduction of carbon monoxide and 25% reduction of hydrocarbon. So that is actually good and with significant emission reduction. We submitted this report to the Supreme Court, and we are waiting whether mass transformation of all CNG buses in Delhi will be done with CNG. So this is one demonstration I see it, and these are the some infrastructure we have. We have the electrolyzer, compressor, and we store hydrogen 500 bar, which is safe at our site. And these are the summary of how many dispensing stations still available in India, because time is less. So let's talk about fuel cell. It's a river of electrolysis. So where you can achieve more than 60% efficiency, and whereas in the ICNG thermodynamic efficiency can achieve maximum 25%. So look why we are talking about fuel cell technology, although the cost is very high. So with that, as India do not have any technology of fuel cell or storage of hydrogen like composite cylinder, we started working on fuel cell development, and we have demonstrated many small 40 and cycle fuel cell which we are working, and we are working in Lucknow. This is one of the first Make in India institute on hydrogen. So there, it's a project by government. We are spending about 200 crore this project, and government is giving us 100 crore, where we demonstrate all the hydrogen production technology like biomass gasification, like electrolysis technology, then reforming of bio-CNG. So all green hydrogen, we will compare the cost and we will submit data to the ministry which will be suitable for India. Then on storage part, we are working with composite cylinder, which is type 3 cylinder. Also, and we will use those composite cylinder in the buses. And we are working on Tata Motors to develop 15 fuel cell bus, and in these buses, fuel cell will be developed by us. Some of the buses will commercialize fuel cell stack, so that we compare the data also. This is actually, we say, the first time in India in the world to evaluate all fuel cell of hydrogen. So this is high proper. And for blue hydrogen in our Gujarat refinery, we have placed a dispensing station so that we can sell blue hydrogen. So storage part, I think I will go. These are the prototypes we have prepared. We are working with IIT Kharagpur to type 3 cylinder. There is an aluminum over which you can wrap carbon fiber and to store hydrogen 700 bar. If you use the metal cylinder for 700 bar storage, the weight will be so huge that the weight of the carbon. So they use storage story. So the government is in the climate, we want to control it, and the same government of the solution, and we have to burn out dry and green hydrogen and blue hydrogen, and we have the facility for the renewable gas and transport mechanism, transport mechanism. Then other hydrogen pathways like biomass facility can help us to meet the climate mitigation. Thank you.
Very good presentation from Tapan Bera, and I am sure many questions should come from audience, and so far as we have said is concerned, on the dais, one expert is here. He will be able to answer your so many queries along with Tapan Bera. Now, without any formal introduction before, I would request Devji, because of the fact I already have given his introduction. So Devji.
Respected dignitaries on the dais, Dr. Baju, Kapun Bera, special thanks to Professor Ashwin and Dr. Sharad, my teachers and professors of this college, my junior members, students, research scholars of this university. It gives me a fantastic feeling to deliver a speech to you as I was a student of this college from 20 years back. So I could recall my days. When I started my career about 20 years ago, the circular economy or sustainability, these are good to know kind of subjects, buzzwords in the industry. But in today's world, this has become absolute necessity of current world. To reduce the landfill, to reduce the waste, to reduce the energy consumption, to reverse the climate change, this has become absolute necessity. So I work in a company called Drop Guitar, which is engaged in the hydrocarbon sector, upstream and downstream. And we provide chemical solution to these companies. We say like innovation is in our DNA, and the company always invests a large amount of money for the innovations and find out the right solution to increase the sustainability. So with that, I will start my presentation. So I have actually 3 subjects. One is how to create more value from plastic waste. The second one is the safe sulfur for the ethylene furnaces and the hydrogen catalyst. And the third one is called a chemical called DNPP replacement for styrene plant. So I will try to make justice to the time given to me, 25 minutes. If there are questions, if time remains, we will answer. If not, we are there for the 3 days. We are having a booth also, we can answer it. So waste plastic disposal is a global problem. So globally about 300 million metric ton plastic is produced, and you can take about 9 to 10% is going to the recycling. There are ways of recycling plastics. One is the mechanical or the physical way, and the second one is the chemical recycling. Now where DOF comes in, how to create a differentiating technology where an existing asset of a refinery can be utilized to generate more value rather than other chemical recycling process. So if you follow this diagram, what do we mean by a circular economy for plastic? So we have a oil refinery, we get naphtha, we go to a ethylene furnace from naphtha like naphtha cracker, we get ethylene monomers, maybe styrene monomer, then we have a polymer, then it goes to a landfill waste, and then to a chemical recycling route we get to the oil. So basically, if we follow this cycle, we could actually reduce the usage of new oil. We are actually cycling the process. So this is circular economy for plastic. Now, if you follow this, this is something the comparison about the physical mechanical
recycling and the chemical recycling. So from a fossil fuel manufacturing plant, end user like us, it is going to a waste. For physical recycling, going to a landfill, mechanical recycling, lower value plastic, and this cycle goes on. So a lot of manpower is involved here and a lot of pollution related issues. For a chemical recycling from waste, it goes to a chemical recycling plant, almost a virgin equivalent plastic, and then the manufacturing product. So this is a chemical recycling. Now, you all know that polystyrene cups are losing market share because of the difficulty of recycling it. And segregating is also an issue. There are two processes normally very popular globally. One is the Agilex process and the second one is the lax process. Because of the difficulty of time, I will not cover very thoroughly on this, I will just touch. So this is basically the flax pyrolysis process. So those who are from the refinery, this is close to an FCC unit. You heat it, pyrolyze the plastic, and then you get something kind of oil which is known as flax. So from there you could generate another form of plastic. So it is not getting actually waste. Now comes the technology. Why we have invented this technology and where is the difference? For a kind of pyrolysis technology like Agilex or a flax plant, it requires a huge investment because we have to put down a huge plant, huge investment, huge capex investment. A lot of CO2 emissions would be there because we are heating it. About 600 degrees C we are heating it. So a lot of temperature is required and a lot of CO2 emission because of fuel oil or fuel gas burning. Not in my backyard. So this is an American English. It says if a lot of CO2 emission is there, a lot of pollution, a lot of getting approvals from the government, sanctions. So people will not allow this kind of plant in their backyard. So the payback periods for this becomes very high. So it is not attractive to many industries. Now, how the differentiating technology, why Dovetail invested in this technology? We have a unit in the refinery called cooker or visbreaker, which is basically a bottom of the barrel upgradation. From the VR residue, it goes to a cooker or a visbreaker. So we utilize this existing asset. These terms are very famous in the industry. Asset utilization, asset integrity, asset sweating. So we utilize this asset like a cooker and we mix this waste plastic with VR in a ratio. And we use our additive, dot chemical additive, to improve the distillative. Because the bottom of barrel, I mean the VR, when we send to a cooker or a visbreaker, my intent is not to prepare the coke, to increase the distillative. So if we increase the distillative, we will make dollars and dollars profit to the company. So we did an extensive research on this and blended plastic was used as vacuum residue. I will come with the results. And comparing the baseline with actual result, I mean we did a lab study in a pilot plant where VR was mixed with polypropylene and we generated the temperature and we saw how much is the distillate heat and the coke heat. And in another sample, we did the same ratio, we mixed some additive and we checked how much is the distillate heat and how much was the coke heat. If you look at this chart, this is 100% here, so we are getting about 34% light distillate, this middle distillate in gas oil fractions. From 100% propylene, this is the chart. This is the 50% here, 50% polypropylene if we process in a cooker. So you are getting about 14% light and 49% middle distillate. With additive, the light distillate increment is so much. We are increasing by 20%. So it is millions and millions of dollars if we implement this technology for the company. If you look at the coke generation with baseline, this is 50% polypropylene and 50% plastic. So the coke generation was 25.2%. If we compare with the sample where additive was used, the coke reduced, which is better. Lesser here is better because coke is not the desired product. For a cooker, coke is a byproduct, not a product. It's not desired. If we increase the distillate, we make billions of dollars for the company. So, in summary, chemical recycling is a new process. A lot of innovation, R&D works is going throughout the world. There are processes available for chemical recycling. Where Dovetail comes in is with additive, you could utilize your existing asset of a refinery, not investing in any billions of dollars in capex project, and you get a good distillery. At the same time, you could reduce the plastic waste. So I move to the next topic of the subject, DMDS replacement for hydroheaters and for the ethylene furnaces. We are calling this technology as safe sulfur. So I can find in this auditorium many people who has actually used this technology. Shamunda has used this technology probably in his plant. So just for the students and other stuff, so in ethylene furnaces, this is a cycle. We crack either naphtha or gas, coke is formed, HSSB is hot steam standby. We do a passivation by a chemical called DMDS, this dimethyl disulfide. It's a popular chemical. And then the cycle goes on. The problem is when coke is formed inside the tubes, coke is not a good heat transfer medium. So your heating on the fuel gas will increase. You have to find more fuel. So tube metal temperature increases. So the acid reliability of this tube decreases. Oil pressure ratio increases. The furnace run length is a limitation. Why coke is formed? Coke is formed due to two mechanisms. One is catalytic and one is thermal. The tube metal temperature increases, the coil pressure ratio increases, and since the coil pressure ratio increases, the furnace run length decreases because of reliability issue. The furnace has to be taken or shut down. Often plant throughput is reduced. So if firing is going more, you will reduce the throughput of the plant so as to control the tube temperature. Coil metal alloys, in this comes the chemistry. Nickel accelerates coking. So the technology of DMDS is based on we passivate the nickel sulfates by nickel sulfide and so as reduce catalytic coking. We cannot control thermal coking, it will happen. We can control catalytic coking. Now DMDS has been used through ages, through decades. The problem with DMDS is it does a good furnace sulfidation. The problem with DMDS, it is not safe. We will compare the properties. The main problem is handling issue, storage issue, dosing issue. It has a very low flash point, about 15 degrees C. It requires a nitrogen blanketing, regulatory transport is required. It has a very bad smell. So a lot of HSE issues are there. So Dr. Engg invested a lot in this technology and invented a molecule based on a polymeric sulfur, I think a high molecular weight, about 230 gram per molecule compared to about 94 gram per molecule of DMDS. The order of this is much lesser than DMDS. So in terms of HSE benefit, it is much higher. If you compare the properties of Salsafe and DMDS, I can tell you that globally we have at least done programs with the sulfates across at least 12 plants globally. In Southeast Asia, in North Asia, in Brazil. And in fact, we have done a pilot plant study in a very reputed institute globally, which is Ghent University. Those who are from petrochemical, in 1 month they can identify this university. So where we have seen, in majority of the plants, we could get an actual improvement in the C4 rate. This is dollar for the petrochemical company, increase in the C4 rate. Furnace run length will be extended. Less CO generation. If you produce less coke, less CO generation. Hydrogen makeup will be less because if carbon monoxide is less in your methanator, your hydrogen makeup will be less. This is another important aspect. Carbon disulfide generation is less. Some people say like carbon disulfide is a poison for PGHU catalyst, but definitely carbon disulfide is less produced than this. All these are HSE benefit, handling issue and the smell issue, there is much less toxic. So HSE benefit, reliability and profitability are the main USPs of this change. Now these are from the actual case studies of the plant. This is a mixed with cracker of a numerous design. If you follow this pink line, this is the run length was about 30 days. So when this Salsafe was introduced for this technology, the run length was increased by 33%. So there is a lot of dollars for the petrochemical plant. If you follow the CO also, carbon monoxide is a bad thing. In your methanator, hydrogen makeup will increase and it is also a poison for acid acetylene converter. So from 0.06 mole percent it reduced to 0.02 to 0.05. It is very important in terms of a reliability point of view because catalyst is very costly. Second case study is Stone and Webster design. So the run length was varying from 10 to 60 days. When sulfate was introduced for this plant, the run length increased to 67 days. So definitely the improvement was maximum from 10 to 40% improvement. A lot of improvement in the run length. So this is the next area where sulfate can be used. This is a hydropeter catalyst. So those who know about a refinery, they are well acquainted. But for the students, in a hydropeter, in a refinery, we have a naphtha, we have a middle distillate, we have a hydrocracker. Everywhere you need a catalyst, and normally the catalyst is COMO type of catalyst, cobalt molecular. Now, COMO type of catalyst in their sulfided form can only desulfurize. Basically, you desulfurize a naphtha or a diesel to make it user friendly and to lessen the pollution. Now, cobalt and molybdenum in their only sulfided form, cobalt and molysulfide can only desulfurize a fuel. But the issues of supplying with cobalt and moly in sulfided form is pyrophoric. Pyrophoric means when you come in presence of oxygen, it will catch fire. Though some technologies say that it can be supplied in sulfided form. So the refinery gets the catalyst in oxide form, and with DMDS they sulfide this catalyst in situ. Like just before putting the diesel on stream or a naphtha on stream, they will use this DMDS in a very high dosage and passive and sulfide this. And normally they monitor this by the H2S plateau. They got about 3000 ppm in the recycled hydrogen gas. When it is reached, they will feel like sulfidation is complete. Now these are the problems. If you follow this, DMDS has a flash point of 15 degrees. The skin irritation is 7, 6 is higher. Here higher is bad. The odor toxicity limit is 250. Here lesser is bad, it is more lethal. Small causes more danger. Nitrogen blanketing is required. It requires a regulated transport and odor is very bad, rotten. If you compare a sulfate, like the flash point is 65, from 15 to 65, it is much safer. The skin irritation is 4 and 2, much lesser than this. Here lesser is better. The odor toxicity limit is 5000. So basically 20 times less lethal than a DMDS. Nitrogen blanketing is not required. No regulatory transport is required. And odor is much lesser. So this is typically a DMDS dosing system. You require a nitrogen blanketing, a lot of other stuff. And this is typically a sulfate which is dosed in a refinery. This is our supply ports and this is the dosing system. Simple dosage system. No specialization. Now, how this technology is better than a DMDS? Now, DMDS is not safe. You require a lot of, like a sophisticated dosing system and a regulated transport. In case of a sulfate, you require a vanilla kind of dosing system, no specialized system. Now, sulfate, it has been found that it has a high laydown efficiency. So, it is believed that if you use the sulfate in a catalyst, it could improve the hydrogen purity of the recycled gas. And the immense importance is the ATC benefit in sulfate is much higher. So these are the main USPs of sulfate. So this product has not been utilized in plant yet. We are in the alpha testing phase. So we have done a testing in a pilot plant in IIT Dehradun, where we have getting tremendous result of this. We are looking for the industry partners to commercialize this technology. I will go to the third paper, which is DNPP replacement. So DNPP is 4,6-dinitro-2-secondary-butyl-phenol. So I utilize my chemistry skills here. It's a long molecule. So this is styrene. This molecule is styrene and this molecule is dihydrogenazine. So what happens, like why styrene is important? Styrene is the main ingredient for styrene butadiene rubber, which is the main used in the tire industry. Now in styrene is defined by Lamas process or Bayer process. by dehydrogenation of ethyl benzene. The problem in this process is styrene also can co-polymerize with diethyl benzene and itself can react to form polymeric product. Now if polymer is formed, it is a loss to the company because there will be huge tar and styrene loss will be there. So we have to reduce the polymer formation for a styrene plant. Now there are technology available globally. Now where DOF comes in, we invented a patented technology where we can increase the reactivity and reduce the polymer formation, and as well as we can optimize the dosage of polymer inhibitors and reduce the cost. So styrene polymerization accelerates by temperature residence time contaminants like diethyl benzene and iron. Now there are two kinds of technologies people uses there. Some plants, what I have seen, uses a true inhibitor kind of technology, and some plants uses a retarder kind of a technology. Now true inhibitor provide great performance. Like if you have a proper dosage in the system, slightly excess, you will provide a great polymer inhibition. But the problems start if there is a power shortage or power out in a plant. You will not have any chemical, and then the problem will start. It will be a huge polymer formation. The second chemistry people uses in the petrochemical plants, in the styrene plants, is called a retarder. Now retarder provide a steady protection against the polymer formation. So in case of a shutdown, other things like the chemical would be there to provide the protection. So some plants globally, like we have globally about 26 million metric ton of styrene production, mainly concentrated in Southeast Asia, Europe and Middle East. So some people uses a inhibitor kind of chemistry, some people uses a retarder kind of chemistry. Now where DOF comes in, I will cover in the next slides. So something about the chemistries here. So this is the polymer formation. If you do not dose any chemical, the polymer formation will increase like exponentially. So if you have a true inhibitor, polymer formation is very less. Now suppose you do not have any chemical, the polymer formation will again increase. So the retarder chemistry is based on it will provide a steady protection against the polymer formation. So that's why some people use a retarder. DMPP is a bad guy. So the oral toxicity limit is extremely small. It is very lethal. So you can understand, like 1 teaspoon for a 70 kilo person is lethal. You will die immediately. Chemically, yes, it is better. It has a high thermal stability, good protection against even the divinyl benzene polymer, and it is low price. It is cheap. But here is the debate: cheap against sustainability. So there are technologies available, but where DOF comes in, DOF has a patented green retarder. We call it Actify, and we use this technology in styrene plant. You can use this in butadiene plants. We use it in lightens, in the petrochemicals. The oral toxicity limit is much higher. Here, more is better. It is less lethal. It has a very good thermal stability, excellent. Now it has been found that with a very less amount of activator, if we add a very less amount of activator, and there is the technology. These are all the patents which DOF has filed regarding this activator. If activator is used in this green retarder, it increases the reaction rate by much amount, and it has been found that the polymer level also reduces, including the divinyl benzene copolymer. So what are the USPs here? So DMPP, why it is bad? It is carcinogenic. So green retarder, according with this activator, it is non-carcinogenic because it does not have any nitrogen molecule there. So NOx emission is also very less. It has an enhanced polymer inhibition quality, so your human run length increases and lessen loss. In case of a power shortage, it provides a tremendous amount of reliability to your plant. So this is some of the actual case studies of Badger design. Badger is an important licensor for a styrene plant. So if you follow this graph, I'm sorry that the letters is difficult for you to read, but this is actually the tar formation. The plant was using a different chemistry, which is about 14.1 kg per ton of tar polymer was getting produced. So when the plant shifted to this Actify technology. So the current reduction was about from 14.8 to 14.1, a great amount of reduction because if you consider the total capacity of the plant. The second graph is styrene monomer loss, which was about 1 ton per hour was getting lost, and with the difference of the technology what we implemented there, the polymer formation reduced to 0.6 to 0.7, 30% reduction, which is a lot of money, and this plant would save millions of dollars. This is the second case study of this technology in the EV splitter. EV splitter is ethyl benzene splitter, which is downstream of a styrene plant. So they were having a high polymer, about 400 ppm. With this implementation of technology, you could see the polymer formation was reduced by at least 50%. So in summary, DNTP is a popular molecule which is used in the styrene plant as a retarder type of chemistries. There are other green retarder type of chemistries available globally. Where is DOF metal different? It has invented a molecule which, when introduced in the green retarder molecule, we call it Actify, it could enhance the polymer inhibition and provide a great sort of reliability. Thank you. Thank you. I think I have made justice to the time. Please go ahead.
They have done a fantastic job, timely completion, etc. And I strongly believe after this lecture, Devji will find some client. Jayanto, am I right?
Some
Someone?
some polygons.
Okay. So Devji, तुम्हारा काम बहुत बढ़िया हो गया. अभी तो है. Professor Sundar Basu will take it one page only, one slide. He has forgotten to present the acknowledgement. So let him finish first.
I headed a institute. I'm a director of that place. So what I do is based on the earning that we have through different industry. This slide was the last slide. I thought by question answer session I will be allowed to put this slide, but of course that was not there. So just wanted to point out that I am from a CSI lab. You must be seeing in many newspaper and many places that we have to earn on our own. So if we earn about 40% of our budget, so if we have a 100 crore budget, actually we have about 120 crore budget per year, and we earn another 40% of that budget through this, all this industry participation. Left hand side, of course, some of the ministry. I'm not considering ministry fund, but I'm considering all the fund that we see, JSW or Jindal or L&T or Tata Steel or whatever. So we earn 40% of our total expenditure per year through our in-house generation, and that is how we sustain. Thank you. And one more invitation, my personal, I will be soon back to IIT Delhi. So I would like that Technology, Haldia Institute of Technology, but I don't have anybody from here. I have from NIT Durgapur, I have from NIT Suratkal. So they are doing BTech there and they are doing PhD in my place. And direct BTech and then PhD is possible. If you want to do MTech and PhD, fine. If you want to do BTech and PhD, also fine. In my institute, we take directly, but you have to, of course, give GATE. There is no shortcut. You have to qualify GATE. Not only that, you have to be at least within the boundary of the GATE that last MTech students have taken. So if the last MTech students taken 500 score of GATE, you have to have 500 to get admission to PhD. Minimum. You can take admission to MTech, but you can take direct admission to PhD and you can do PhD directly after that. So you are most welcome to come. You know the scholarship, which is a huge amount, and if you earn CGPA more than 8.5, you can get PMR, Prime Minister's Fellowship, which is 75,000 rupees per month plus HR. It comes to about 1 lakh for a PhD student to get the fellowship per month.
ছেলেপেলে বলবো চাকরি না করে শুদ্ধর কাছে পিএইচডি করতে যাও, কোনো অসুবিধা হবে না, খেয়ে দিয়ে ভালোই পয়সা বাঁচবে, পিএইচডিটাও হয়ে যাবে। অসীম পেছনে তারা দিচ্ছে, আমার কিছু করার নেই, আপনারা মাফ করবেন, বসতে না আর করতে পারবো না। We have concluding session on 24 and I will request all of you to meet the speaker of this session during lunch time to meet your queries, what you have in your mind. I would thank all the speakers, Sitosoto Vasu, Devjit Chandra and Dr. Tapal Bera for their presentation over here.
I'm sorry because we are running late. Actual lunch break was at 1 p.m. We are running nearly 30 minutes late. So those who are they are in the online meet, so they are also suffering with us. So now I would like to request our students, Community Soccer, to hand over flower bouquet to our special chair, Professor Paul Shabay. Thank you, Professor Vasu. Dr. Tapal Bera. And to Mr. Devjit Chandra. So now we take break for lunch. We have only lunch packets, so I think it will not cost more time, half an hour. So we are targeting that we will be here at 2 p.m. so that we can run exactly whatever we have to do.